I'll begin.
Recording in progress.
Hello,
There you go.
everyone. We're Theoretically Podcasting. This is your host, Vasu Sham, and today I'm joined by Dave Sloan. Hello, Dave.
Hi, Vasu. Good to see you.
So Dave is a professor at the University of Lancaster. So could you please walk us
Senior
through?
lecturer.
Okay.
In the UK,
Yeah.
we have professor is like the equivalent of like full professor or distinguished in the
Uh-huh.
UK. So I can't, I'll get stomped on by my head of department if I start claiming a rank I don't have. But yeah.
Yeah, well, you see, start by doing that in America. It's a little bit different, but okay,
Yeah.
you'll catch on. Uh, so yeah, Dave, you're also involved a little bit with the FQXI.
Yep.
So could you tell us what exactly you do for FQXI?
Yeah, so I think my job title is Science Programs Manager, but at FQXI, we're a very sort of small but flexible organization. So you sort of take on a lot of roles. So
Mm-hmm.
what I do is a real sort of mixed bag, all the way from organizing the conferences and getting people to do things like grant review, looking through grant proposals, through to fundraising ourselves. So sort of going to people and saying, hey, can we have some money to do some great physics and sort of look at some of these fundamental questions, which is what we're really interested in.
Nice. So for context, I met you the first time at a shape dynamics workshop.
Yep.
And most of my listeners, I suspect, won't know what shape dynamics is, and a Google search will not help them all that much because, yeah, I mean, you'll find some graphics design thing before what we're actually talking about. So
Sure.
perhaps we could start with mentioning that your background is actually in cosmology. So how did you find your way to this thing that is that is called shape dynamics, and then we can also explain what it is. So
Yeah, so I like to think of myself, I mean, this description gets worse as time goes on, but I'm a mathematician that got lost.
okay.
As an undergrad, I did a master's in mathematics, and then I went on to do theoretical physics because I found that all the problems I liked in the areas of maths I liked ended up being physics problems.
Mm-hmm.
So it was fun. So I did my PhD in loop quantum gravity, in loop quantum cosmology, which was sort of growing at the time.
Mm-hmm.
I mean, it's still a growing field, but it was sort of a really sort of interesting time. And I worked on problems like inflation in loop quantum cosmology. After this finished, I went and, the typical route and doing a couple of postdocs here and there. And it was whilst I was doing one of these postdocs that I got in touch with Tim Kozlowski and Flavio Mercati, both of whom I knew from sort of Loops days, who were working with Julian Barber on these ideas of shape dynamics. And we sort of realized that a lot of the ideas that I'd been looking at in terms of how there was these sort of interesting symmetries in cosmology, which is something we'll probably talk about a bit later, could be applied and sort of give solutions in the approach they were taking to the cosmology of shape dynamics. So we sort of
Right.
got together and got to working on this. And, I'm sure you know how it is when you work on a really cool problem with people who are sort of as nerdy as you are about that problem. You have just a great time. And we sort of had this great atmosphere. It was a very productive time.
Nice, nice. So yeah, I guess we should also briefly describe what shape dynamics broadly is, which
Yep.
is it, I mean, narrowly, it's a kind of modified gravity theory that locally is indistinguishable from general relativity. But what it does is it trades sort of one component of the diffeomorphism group, so to speak, for lack of a better way of putting it. That is the one that has to do with the refoliations of space-time. I mean, if you decided to do a split, then general covariance tells you that you shouldn't privilege one foliation over the other. But shape dynamics trades this for a local spatial Weil invariance. And
Yeah.
depending on how technical we are, it started life as Weil transformations of space that preserved overall volume, and then get a little wiser and you realize that you can actually have a version of the full Weil invariance based on what you call your Hamiltonian. It also has a sort of broader, more general sort of theme behind it, which has to do with recasting various dynamical systems in terms of the dynamics of only the shape-like degrees of freedom. So it's not restricted to its application to general relativity, but oftentimes it happens that the one use case in the GR setting is kind of, you know, synonymous with the more broad with the more broad idea. And a lot of its construction was due to ideas of Julian Barber, the progenitors of this. Sort of, yeah, I was thinking about this general questions of like time and motion for like a million years, and then came out with this insight that the things that change are the shapes.
Yeah, I
So
mean, I should
yeah,
say that the sort of introduction you've given there is absolutely correct in what I think of as being sort of the version of shape dynamics you'd get described by Tim Kozlowski, Sean
mm-hmm.
Cribb, probably Enrique Gomez
Enrique
as well.
Gomes, yeah,
Yeah.
yeah,
Um, and that's absolutely true. I think Julian would probably give you a very different spin on things. He'd say it's
right,
an application of Mach's principles
mm-hmm.
at a fundamental level. The idea being that you are trying to describe the dynamics of objects relationally without ever referencing an external notion of scale. Um, it turns out these are completely compatible, as you know, because you're looking for Weyl invariance and so on. So you're looking at objects in general relativity which don't reference scale. Or if I change
Right,
my notion of scale, they're going to be invariant under that transformation. And certainly this is what I think informed the symmetry trading arguments and so forth.
right,
Particularly if
right,
you look at the sort of the earlier work, we're looking at surfaces of constant curvature and things like this. So looking at York time as your parameterization of your theory. But I just want to say that it has sort of both a technical mathematical foundation and a very sort of strong influence of the philosophy of physics behind it, which is
right,
kind of
right.
nice.
Indeed, indeed. And it was the fact that there's this underpinning, like this Marx principle underpinning everything, that made it such that the idea was applicable much beyond the narrow realm of gravitational physics writ large.
Yeah, sure.
And I guess one of the offshoots of that is what we're going to talk about, which is
Yep.
dynamical similarity. And
Yes.
and here we will see how we can kind of go between cosmology, the Kepler problem, like, just mechanical systems, the harmonic oscillator, and maybe
We'll
even
probably stick to the harmonic oscillator, but
let's
yeah, we can
yeah
handle
let's
Kepler.
not get too,
Yeah.
yeah, let's not get too ambitious. But what I do want to also discuss with you is how some of these ideas can interface with some of the things people do in statistical mechanics and in quantum field
Sure.
theory, just because there it just seems that what is valued most are just methods, rather agnostic to any kind of philosophical underpinning.
Sure.
And just because it's notoriously hard to make sense of any kind of principled sort of philosophical story that one can tell in quantum mechanics. Although a lot of people would disagree, I'm sure. But
Well, I mean, I'd say in a lot of cases, there are principles at work. You
right,
just may not be, they may be sort of subconscious bias
exactly.
principles, right? Everyone has
Yes,
their own set of aesthetics that they are implicitly applying to a theory.
right, right.
But
And I think that
sometimes,
we'll,
yeah.
yeah. I mean, I embrace this sort of sleepwalking attitude
Sure.
in
I mean,
that area.
it is actually one of the most interesting things when you start talking to people who do philosophy of physics is they sort of pull you up on this and they're like, hang
Right.
on, you're making this assumption, and you sort of think to yourself, well, that's blindingly obvious. And then you realize that what you think is absolutely obvious is not something that everyone else is assuming. And it's very nice sort of when you do this, because you start realizing why you might be reaching some sort of pushback against your ideas, or people might not be following you when you make a leap, because underlying this, you've made an assumption that you've sort of inherently gone, well, everyone must think this. And then you
Right.
realize a good fraction of people don't.
Indeed, indeed. So I feel like I feel like here what we're going to do is go over this nice little mathematical realization of a symmetry principle. It's a little bit more general than a symmetry principle, I would say. It is a symmetry of something,
Yeah,
but
yeah, yeah,
not of the things that we normally
yeah.
associate with. And then we'll see that there's a trick that it rhymes with, and so let's just get into
Sure, yeah,
the heart
let's
of it for the time being. So
dive into the
I'm
weeds. Yeah.
basically going to review this paper of yours, titled Scale
Okay.
Symmetry and Friction. And well, I thought that the easiest thing to start with is the sort of slight modification of the action principle that you advertise, which
Yeah.
was first, I guess, conceived of by Hergloss. I'm not even sure. Like, what is the etymology here? Like, where did
Yeah,
this?
Herglotz is
Who did
German.
this come from? Okay.
Yeah, so this idea is it's a modification of the usual Euler-Lagrange
Mm-hmm.
ideas by I think it was Gustav Herglotz
Mm-hmm.
in about the 1900s. And he made this one sort of small change to action principles, where you think an action is an integral of a Lagrangian, and a
Mm-hmm.
Lagrangian depends on some configuration space, maybe some velocities, etc., on that configuration space. Herglotz allowed the Lagrangian itself to have the action as an argument. And so it's a bit like saying S dot is a function of Q dot, and S, the
Mm-hmm.
action S. And so you've just
Okay.
sort of introduced this extra factor where the action itself can now play a dynamical role.
Right, right. And that is very confusing at first sight, but let's just learn the
Yeah,
rules, I guess.
I mean, it sort of, when you first look at this as a physicist, you go, what on earth is going on here? But then again, you think about it like a mathematician, and you go, F dot can be a function of F. Yeah, I'm happy with that type of system. In fact, those differential equations we're quite happy with.
Right.
Uh, so
Right.
it's,
And
yeah,
I guess that this okay, so the first example will make clear when this kind of thing is useful and what it can
sure.
account for that regular action principles can't.
Yeah,
But what we're building towards is a is not just a description of these frictional effects in dynamical systems. We're interested in sort of frictional effects that arise as a consequence of, modding out by scale transformations of a certain kind.
yeah.
So
We'll
that
get to them, but
that
that'll take us a little
yeah,
while.
yeah. So for now, let's just go through the motions. So we have
Sure.
S depending, okay, so the Lagrangian modified to LH, which now depends on S, the action. And here are the rules. So you vary that whatever SH for its
Yeah,
equations
sure.
of motion. And you're left with the following, which is almost the Lagrange equation if we ignore this last term, but then this last term introduces a frictional effect.
Yeah.
Cool. And so it does lead to what would lead to like non-conservation of energy, for instance, if we were to just look at some simple examples, as we will. And hence we're calling it frictional.
Mhm.
And the equations of motion written in terms of Hamiltonian now, which you can get by doing a Legendre transform in much the same way to LH, thinking of all of these as being dynamical variables gives you the following. So S has this dot here. So in addition to the equations of motion for Q and P, we have this S dot. And again, we'll note that the forces are now modified by this extra term. So this is kind of the novelty. The Hamiltonian is not conserved exactly because of the dependence on S. And here we see an odd number of things, Q, a Q dot, and an S. And as such, we can't usually put this all into a symplectic form because we need one extra dimension, which is what becomes part of a contact geometry. So that's what the symplectic geometry is replaced by, is this contact geometry, where instead of the symplectic form, we have a contact form, which in local coordinates is minus ds plus what you would normally call the symplectic potential. So this isn't the symplectic form, this is a symplectic potential, the d of which is a symplectic form. And as such, this being ds will mean that if you take d eta, then, well, this will vanish. The d acting on this will vanish, and you're left with the symplectic form as you would normally have had it. So that's kind of how all of this works. And thing is that the non-conservation properties of the Hamiltonian and, well, everything else will imply that, in fact, we have this kind of evolution of eta. So in much the same way that, you have the Hamiltonian changing here, that's exactly the prefactor of how eta changes when you take a time derivative. So it's proportional to the volume form, and you have, well, it's proportional to eta, or, if you look at the volume form's evolution, it's proportional to the volume form with this prefactor. So this dh, das is kind of the offending term everywhere, right? It's kind of the universal sign of trouble. But it's also the sign of the novelty of this situation.
Yeah.
So that's kind of what's cool about this. So here it's not like you have a deterministic evolution dictated by something like Liouville's theorem for the, which is given by the conservation of the actual volume given by the wedge product of the symplectic form to the appropriate number of dimensions. That's just straight up conserved. So phase space volumes are conserved, and that dictates, well, all of like classical many-body physics or kinetic theory, right? So that's kind of everything. Here we're actually baking in to the system a non-conservative effect, right? So this is a bit different from what we do in kinetic theory, where we just sort of look at various n-body distributions, and then we just kind of truncate the hierarchy that results from Liouville's theorem. We just say, okay, we don't know because we just can't, and therefore we have the Boltzmann equation. Here, no, you actually have a non-conservation, but it's relatively well behaved. It's not coming as a result of any approximation per se. I mean, it could be related to one, but as such here, it's all just in the dynamics that you have. You see this focusing or spreading effects that we will come to understand now. So this is all very cool.
One thing I'd add here is that you use the word deterministic. So this system is still entirely deterministic.
Correct.
You give me a q dot, an s at some time, and I can tell you them forever.
Good. Yeah. So that I think is also worth saying, that it is in fact all deterministic. There's no noise as such. And it's not like there's a truncation effect either that's giving rise to
no, this is an exact dynamics of a finite dimensional system, which is autonomous. Right.
And already here I can kind of see why you as a cosmologist might have been drawn to this, because I mean, well, let's just get to that. I mean, maybe you don't want to spoil it at this point already, but perhaps
I mean, I discovered this backwards, right? I mean, I started working in cosmology and doing these weird things there, and then had to backtrack and try and find what was going on with the maths afterwards.
Yeah, and I mean, if we get the time, or if we decide to go in that direction, it would be very fun to hear some of your thoughts on how some of the wisdom you gain by meditating on all this informed your some of your work on the measure problem, for instance, where I do think that this, I mean, like, these are the kinds of things that people should have thought about. But it's great that you're on that too. But okay, so let's do all this with the harmonic oscillator, our atom of understanding, out of which we build everything else.
We're physicists. We have to do a harmonic oscillator.
And again, this is all just to demonstrate how this Herklotz mechanics works. We haven't gotten to the questions of scale just yet, and so that we will get to. So I'm just kind of like pushing through this with a little bit of haste, only to basically so that we eventually get to that.
I should advertise for your listeners here. If you're interested in learning how contact mechanics works, there are some great papers by Alessandro Brevetti in particular.
Okay, well, you should definitely send me a link to that, and I'll add it in the notes or the description, the video description. Yeah, cool. So what's the motivation? Just to account for sort of non-conservative forces? Is that why they introduced this, or was there some just some mathematical curiosity of what
So I
happens
think
when.
it was mathematical curiosity to begin with. Certainly, you sort of say, look, you've got these beautiful symplectic systems. They're these cornerstones of modern mechanics. Classical
Right.
mechanics, as you understand it as a mathematician, right, is all about flows on interesting geometries. And these flows are brought about by understanding symplectic forms and Hamiltonian functions and so forth. And you generate these vector fields and on phase spaces, and you have this really quite beautiful evolution of these systems. But then you realize you can only handle even dimensional systems with this. And so you sort of say, okay, what is an odd dimensional system that I could, and what are the equivalents and so forth? And this is the kind of thing that crops up.
I see.
I don't know whether Herglotz was actually originally motivated by physical problems or not, but
I see.
as with all maths, it turns out it's got some beautiful applications in physics, which I'm quite happy to steal and try and use.
Very cool. Okay, so let's just go through what the harmonic oscillator does when we
Yeah,
plug in the action. And so, very simply, you just get the equations of motion of a damped harmonic oscillator.
yeah.
And the damping is basically given by this frictional term. And yeah, the interesting thing is that this is just the left-hand side of the Langevin equation that describes the Ornstein-Uhlenbeck process. So it's kind of sort of very basic. It's like the first non-trivial process on top of random walks that you can sort of envision.
Yeah.
And it basically comes from having a sort of random forcing term on the right-hand side. Here we're in the sort of deterministic limit. But you
Yeah.
see the deterministic limit. So basically it's like saying if I took that process, the Langevin equation for that process, and then I just took the mean everywhere. Noise has zero mean. This is the resulting equation.
Sure.
So that's another way to think about it. But yeah, let's
I
just
just
say
think of it
we're
as the
on a
damped harmonic oscillator, Vasu. I think you're being way more advanced than necessary there.
No, it's
But yeah,
yeah, sure. I mean, it's just
but
yeah.
you're
I
absolutely
mean,
right. Yeah, I mean, this is the autonomous limit, I guess, the
yes,
or intrinsically deterministic limit.
right, and yeah, we can comment a little bit more about that. But for now, we get this. We didn't put this in by hand. It came from having the action be part of the Herglotz-Lagrangian, and
Yeah.
then just deriving the equations of motion. And similarly, if you did a Legendre transform, what we have is that in addition to the harmonic oscillator Hamiltonian, which we all know and love, there is this linear term in the action. And the equations of motion now just separate this second order, the one second order differential equation into, well, multiple first order ones, and you get the following. And here there are two changes. P dot isn't just minus kx. There's also this term proportional to mu, and S dot has this term. So I mean, there is a meaning for S dot in regular mechanics. It's related to Hamilton-Jacobi theory. It is just the Hamiltonian. Whereas,
Lagrangian.
sorry, it is just the Lagrangian. Depends on what we're calling the dot, but if you're taking the total time derivative is going to be the Lagrangian. Whereas here, in addition, you're going to have this term because, of course, well, that is what you have here. So yeah, that fulfills the prophecy we had initially to say that dH dt is not zero. It's in fact proportional to h with this parameter mu. Now,
So there's an important point here
yeah,
that gets glossed over a little bit when you do just the math side of this, but you'll notice that the Hamiltonian itself is no longer just the mechanical energy of the system.
true.
So normally, if you thought of the mechanical energy of a harmonic oscillator, you wouldn't have this action term involved. The reason that's important is because this system loses, let's call it Hamiltonian energy, all the
Right.
time, right?
Regular energy, yeah.
And it loses it in a very nice way. I mean, you've got dH is proportional to h, so you can solve this. Even I can solve that as a differential equation. But if you looked at this just in terms of mechanical energy, that isn't what happens, right? You only lose mechanical energy when the system is moving. Friction doesn't act when the system doesn't move. And
Right.
so the Hamiltonian energy and the mechanical energy are two separate entities, and this can cause a lot of confusion as if you're not careful about it.
Sure. Yeah, I mean, like some people just prefer not to use the term energy to the thing that isn't conserved. So here,
Sure.
indeed, the Hamiltonian is not a conserved thing. It
Yeah.
does contain the conserved thing, but in addition to that, it contains this term proportional to mu, which then
Yeah.
gives rise to the non-conservation. But I mean, yeah, I guess you're prefacing this because it will play a role at some point, as in, like how we think about the
Yeah.
regular old-fashioned energy compared to to all this other stuff. So yeah, here you say that solutions to the equations of motion show that the system asymptotes towards the stationary point at the origin. So physically, that means that the frictional terms remove mechanical energy from the system, leaving the oscillator to tend towards resting at the minimum of its potential at x equals 0. And this is actually the reason I brought up the Einstein-Uhlenbeck process and the deterministic limit of it. I can mention it, but let's just go through the rest of this for now.
Sure.
But it's also the fact that the volume form on this contact phase space is still a phase space. It's the fact that it's a
Yeah.
contact manifold is a second order fact. But yeah, this 3 form is not conserved. You actually have it decaying again with the rate set by mu. So mu just always appears as the rate at which things that would otherwise be conserved aren't.
Yeah.
The rate at which they decay.
Sure.
So the volume of the contact phase space over time of a set of solutions will reduce, and all the solutions will asymptote towards the same endpoint, and so the volume should contract to that point. And this is actually very visible if we did take the perspective that what we have here is like the mean motion. So it's like the deterministic limit of a stochastic system, because there's another perspective you could take, which is what happens to the probability distribution over x. Like, if it were a stochastic system, you could cast this in 2 ways. You either talk about the Langevin equation that every position individually satisfies, or we talk about the probability distribution which satisfies its own equation of motion. Now, the fact that we have so let's just write it like this. So the fact that there's some okay, well, let's do it for p. Actually, it's just a little bit easier to do since this is sort of second order, but there's basically some sort of simple gradient flow dynamics operating here, right? And so basically you have that there's show p of like some f p x p, right? So that's kind of the structure of the equation. There's no other term, there's no second order term. And then if you ask about like the stationary solutions here, the ones where the left-hand side vanishes, you're forced for this thing to be a delta function localizing onto the minima of this, or the zeros of this object.
Yeah.
And if this thing is a gradient itself, that means that you're localizing onto critical points of whatever appears there. And this thing is going to be, it's basically going to be, the equivalent of the gradient of u, right? So there's like a gradient formula. So f actually equals some kind of nabla u, right? So that is exactly the phenomenon that you're mentioning here, right? So basically this fact that the phase space volume is going to reduce over time is reflected by the fact that the density over the phase space, okay, so really there's something more complicated. I mean, I just took the p distribution, but say it doesn't factorize, it's still true that and so this is just a phase space coordinate. It's still true that essentially if you just looked at the px phase space, setting aside the contact form, this will be either a delta function or a sum of delta functions on the various critical points of u, the potential. And that's just a consequence of there being only drift and no diffusion. If there were diffusion, you would actually get non-trivial solutions. So that's like a fun fact, I guess, maybe something to think about.
Yeah, no, I think there's something as well important here about sort of the physics that's happening as well, because this you understand as being sort of the thermodynamic error of time.
Right.
Sean Gribb and Simon Friedrich have done quite a bit of looking at this in the philosophy literature about how this can be. But basically, if you take sort of Sean's perspective on this, you have a direction in which the system is heading towards one of these fixed points. And once you you see this in thermodynamic systems that are, normal symplectic systems that are coupled to the outside world and so forth, you see entropy increase and systems tend towards these points.
Yes,
And
yeah.
Sean uses this to construct an arrow of time.
Okay, well, that does make a lot of sense. I mean, the the fact that you could have this, so it's a funny thing that if you just looked at the limit of like, yeah, so let's just look at the limit of zero momentum, right? What this looks like. So people would normally say, oh, you have a gradient flow where x dot is given by the gradient of some quadratic function.
Mm-hmm.
And that's obviously the potential energy, but in fact, it is not. Only in the
Yeah,
presence of kinetic energy is that potential, and can you have some
yeah.
conservative force, right? This is a purely dissipative force from the perspective of just mu x dot, right? And
Mm-hmm.
but that is exactly the dynamics you need to reach the origin. Like if you
Yes.
wanted to force one to be able to reach the origin, then what you would do is you'd crank up mu, have this be negligible, and then you would see that the dominant effect is just flowing down to the origin. It becomes an optimization problem with respect to the potential.
Yeah.
And when you have kinetic energy, or when you actually have even noise here, then what happens is that you actually get forced into the Gibbs distribution. So Gibbs
Mm-hmm.
distribution arises at equilibrium because you have noise involved. So diffusion gives rise to that kind of thermodynamic behavior. So yeah, that I guess is something to, I guess, circle back to, and maybe we could even have another discussion about the thermodynamic arrow of time and how you can hook up these different insights. But now let's get to scale, right? So we've so
Sure.
far
Yeah.
been talking just about Eric-Clausen mechanics, plugging the action into the equations, or into the Lagrangian, and how it sort of gives rise to dissipative dynamics.
Yeah.
It's plausible, and we see how it actually happens. But now let's talk about how there is a regular system, for lack of a better term, and our effort to sort of quotient by a scaling symmetry leads us to the kind of system that we discussed in the previous subsection. So here, nothing fancy, just homogeneous cosmology with pick your favorite matter and curvature, leading to the dynamics we are all very familiar with, involving
Yeah.
the Friedmann equation and the actual equation of motion for the scale factor, also known as the second Friedmann equation, for lack of
Yeah.
a better term. And what we'll do now is consider what happens when we do the rescaling of the scale factor and simultaneously the curvature. And this isn't actually a symmetry of the theory, right? So it's not like we have some actual dilatation invariance. I mean,
No.
what we do have is that the action itself changes by a multiplicative overall factor.
Yeah.
Right. So is it fair to say that that's what dynamical similarity always is?
So yes, that's generally how we define a dynamical similarity, as one of these transformations under which you rescale the action.
Right.
Um,
So
yeah.
let's say we have some dependence of the action on configuration space variables, and then we're going to take this to some powers, right? So I don't know what they are, and maybe there is a general formula to tell us what they are, but
Yeah. Sure.
um, for now, I'll just put in a couple of, let's say, let's just prime. I don't know why my typesetter wants to do that. Dot Q.
Yeah.
And then this implies that S goes to lambda to yet another power. I don't have any things left, whatever. S. Okay.
Sure.
So
Yeah.
this is like the general format.
So this is, this is what I would call normally a scaling symmetry. A dynamical similarity would be any general map on Q dot that
Okay.
does this. So there could be
I
more
see. So
complex
this is
behavior,
so this
but
is what matters, right? So as
this is
in,
really the part we're talking about. Yeah, is
I
that
see.
we're
So you're
rescaling the action.
okay. So you're saying a dynamical similarity could just even be like something like this. F of Q dot Q. I don't even know what F does.
Yeah,
And
F and
then
G or
G.
something. So yeah.
Yeah, so the G does something like this too. I mean, I don't know.
Yeah, yeah,
Okay, G
sure,
of
yeah,
Q such
yeah.
that this happens. Okay,
So
and
this is
these are
very,
parametrics.
very general, right? So this
Right.
is, this is one of those things where I mean, it's technically true, but it's almost so broadly defined as to be sort of hard to nail down.
Okay.
Um, the version you had a
But
second ago is what we'd normally call now a scaling symmetry.
right.
Um, and again, this
Okay.
is
Well,
language that, fortunately, working with mathematicians, they've sort of the nice thing about working with people in maths is they force you to really be precise about what you mean by things. And certainly working with Ali Bravetti and Connor Jackman, I've had to sort of tighten
okay.
up my mathematical definitions, which has been quite nice.
Right. Now, what we're not talking about is the scaling of coupling constants just yet. But
No.
I would just imagine that there's some scaling of the coordinates and then, or, of the fields, for lack of a
Yep.
better term, compensated by some scaling of the coupling constants that leaves the action invariant. So that's kind of trivially true, right? You can always do that. There's
This
nothing
can be
preventing
done.
you from
Yeah.
doing that. The issue is that, or rather, what's interesting is when the couplings either don't have to change or scale homogeneously with the volume of space. That's when we normally say we have wild invariance, for
Yeah.
instance, right? So here, we're doing this without particular reference to canonical scaling of, say, the kinetic term or so, which is
Mhm.
the normal. That's, like in field theory, that's the thing to do.
Yep.
Define all relative scaling with respect to the kinetic term. Here, we're not doing that.
Mhm.
So
No.
this ampersand can be whatever it is, right? So
Yep.
that's kind of, so we should preface all of that. So we're not keeping canonical scaling. But anyway, let's proceed to see what the implications are
Sure.
of doing this. So you mentioned that the Hubble parameter is unaffected by this rescaling, seeing as how it's A dot by A.
Yep.
And now you say that we've again extended our dynamical similarity to act on K, leaving the equations of motion unchanged. Because, yeah, of course, if I vary S times lambda ampersand, it really doesn't matter. The equations of motion don't really care. I mean, I would
Well,
just,
you've got to be careful. They're going to change. The equations of motion won't change, but the boundary conditions will, right? So if
true,
you put in
true,
an A0, you're going to have to multiply it by lambda and so forth. So that's
correct,
precisely
correct.
what the symmetry we're trying to talk about is.
Right. Because that is part of the derivation of the equations of motion, is that
Yeah.
there is a boundary term that you do something with.
So perhaps a better way to put that, in, just to edit my previous statement, is it's moving you from a solution with one A0 to a solution with lambda times A0. So it's moving you between
Right,
two different solutions that are related by this rescaling.
right. So I guess we could sort of like write it out. At least in mechanical systems, the boundary conditions of interest are always at some or the other points in time, and normally what you have is delta Q left, right. So you have I'm not sure about the minus sign here, but
Yeah, sure. But I
whatever.
mean, this is the standard of the Lagrange. Yeah. So,
Yeah, so you have this term, but then you also have, as a consequence of having sort of forming this, you have the boundary term,
yeah.
um, which is, it's computed at the two endpoints.
Yeah.
And here what we're going to have is the
Total time derivative. Right.
yeah, what would have been the total time derivative times delta Q
Yeah.
plus whatever else might have come by. Okay, this is like a very basic
Yeah. Yeah. Yeah.
situation. Now, of course, if I were to have lambda to power what did I want? Ampersand here, right?
Hmm.
There's gonna be a sense in which there's a banal nothing that it does on the first term, whereas okay, there's something else happening here, right? I mean,
Essentially,
I
yeah.
need, yeah, okay, okay, cool, okay, okay, great. So let's give matter a shape of a perfect fluid. This is
Yep.
sort of like the simplest hydrodynamic limit to take, the one that we mostly use in homogeneous cosmology.
Yep.
And we have a parametrization, which is also standard, that we take this scaling form of rho with W dictating what rho actually is, like whether it's, you
Hmm.
know, dust, radiation, dark energy, choose your pick. And what we find is that the action, the mini superspace action in terms of this parametrization has the following form. The constants of interest K and W. And now let's go do the Herglotz trick. So I'm going to plug in the action, but what we're going to do is look at, okay, so first, what is the dynamical similarity here? So the hashes, right? Like A goes to lambda A, so the hash here is 1.
Yep.
Ki goes to lambda to the power 3 times 1 plus W. K, just as a consequence of this combination. And overall, this causes the action to be rescaled by lambda cube S because there's an A cube here. So I'm just curious, if I kept G Newton, what would it do? It would be like if a 1 over, it would be
G Newton
somewhere over
in
here.
this case, yeah, you wouldn't have to change, right? Because we've got our KIs essentially. You can absorb every G Newton into a KI effectively here. So it's
Right.
not
No, no,
really
but
making overall. Yeah.
I see. Okay. Yeah. So I mean, the reason what I'm reaching for is like how to relate this. So if I was to give G Newton its canonical scaling, then how many powers of this lambda could I absorb is what I'm wondering. If it's just part of Ki, sure, it does whatever it does.
Yeah, so essentially you could rescale G Newton however you like, right? There's nothing, you have a little issue because some of these, it depends on essentially where you keep your units and everything, right? So I've chosen to try and take G Newton out of this so that we don't have to deal with, okay, this carries units of,
Right.
dimensions of time and so forth. And we don't want to mess around with that too much.
Okay. Okay.
But essentially, look, there's a whole philosophy of how you deal with constants and so forth within the dynamical
Sure.
system, which probably is a little bit outside of our scope. But
Okay.
essentially, what you want to say is something like G Newton for a cosmologist is something you measure. It's not something you're handed, right?
Okay.
And so if you have one of these symmetries and it makes a transformation and it also transforms G Newton, you should transform within your theory what you think the measurement of G Newton would be within that. And so it's not sort of a trivial like this will give you the wrong value or something like that.
Yeah, well, I mean, I guess all scaling is just relative to something. And
Yeah,
you know that the statistical mechanics notion of scaling has to do with, you know, the kinetic term being privileged and everything else scales with respect to it.
yeah,
Whereas here, it looks more that you're doing a certain scaling transformation of the variables, the dynamical, basically some of the dynamical variables and the constants, and I guess what you don't require is that S just remains invariant, right? So like that's like the thing that one would normally do is to say, well, at the end of the day, the action shouldn't change, and that, you know, as a result, you should get your coupling constants to do whatever it is they do to absorb the scaling. But
yeah,
yeah, nevertheless, I think that there's some invariant geometrical things we can think about instead of chasing scaling dimensions.
sure.
Cool. So now what we do is just yeah. So walk us through the trick here. So here's my action. This is analogous to the regular vanilla action,
Yep.
and we're going to plug it back into itself.
Not quite, no.
No?
So that would be quite difficult, right? So what we're going to do is we're going to find a different action
Right.
which reproduces the same dynamics for the Hubble parameter and so forth and the matter dynamics.
Okay.
But that action itself will have A, let's call it A for actions, we've been using S so far, A as
Okay.
one of the variables that's dynamical. And so this
Okay.
is the equivalent of the new Herglotz action. This is the new Lagrangian, let's say. So you want to
Okay.
integrate this dt, for example, to get your complete action.
I see. Okay. Okay. Right. So Z here is going to be this thing. Is that right?
Yep. So Z
Yeah.
is a combination of A and the K.
Little a
I'm
and
going
the
to
K.
little a and yes,
Yeah.
sorry, that's right. Yep, the scale factor and decays in some level. And capital A here actually turns out to be minus of the Hubble parameter.
Right.
This
But
is
the
yeah,
sort of formal intention is for it to be the action, big
yes,
A. It so happens to also be minus H.
yes. Yeah, well, this is
Right.
interesting, right? Because this equation here really is just the second Friedmann equation rewritten.
Good. Okay. Let's
So
do
if you
that,
look at the second Friedmann equation, wherever you had,
which is something like d dot
yeah,
A over A. Well, you know,
you've
yeah,
got it written higher
I'm
up.
not
Yeah,
gonna. Okay, so
you've
it's
got
2H
that,
dot. Yeah.
and
Okay.
then you subtract one of the first Friedmann equations off it or something like this, and you end up with this.
I
You
see.
know, forget exactly
Let's.
what it is,
I
but it
just
is, yeah,
3H squared equals the L sub M.
yeah, plus by
Yeah,
the way,
plus
yeah,
there's a curvature. Okay.
yeah. We can ignore the curvature. I mean, for
Okay,
simplicity, if you
let's
want
just
at this
set
point, k equals
plus,
zero.
let's say k equals 0.
But the first term
Uh,
should be plus h 3h squared.
plus 3h squared. Okay.
I think so at this point in the
Oh yeah,
first
you're
Friedmann
right.
equation. Yeah,
Equals matter Lagrangian.
yeah.
What is a matter Lagrangian in terms of the fluid variables? Well, it's just
Um,
this thing, obviously,
it's just that. Yeah, yeah.
as you've written it down for us. So that's the sum over I, frac k sub I, or I guess you meant kappa. Okay. Plus k I've already set to 0.
Yeah.
3 times 1 plus w I. And then we're saying, okay, this is, if I just do a, h goes to a, then it's going to be a dot plus 3a squared equals this thing, but now
This
this is z to the power
that's
whatever it
yeah,
is.
yeah, yeah.
Um,
So essentially what
yeah.
we've done here is the Zs, you can think about it as we've constructed the elements that are invariant under this transformation. So in other
Mm.
words, if you multiply by, if you change lambda, we want the entities that don't change. So it's a combination of k or kappa and
And
scale factor
that's the
a.
important point, right?
Yeah.
The thing that actually undergoes the dissipative dynamics is the invariant thing.
Yeah.
Good. Okay. So yeah, I guess we could just walk through that. K. So if I divide K by A to exactly this power, since A scales linearly,
Yeah.
then the resulting object will be invariant,
Yeah.
and hence or kappa or whatever, and hence we're left with this thing. And to recover the powers, you have to raise it to this power.
Yeah.
And but there's a dot here. Oh, okay, because let me think. Because it's a
Yeah.
Lagrangian and I've taken a piece of the action, and the only
Yes.
way to get back is that I take the dot. Okay.
Yeah. Precisely.
Okay.
So this
So
is
this
a
is
really
like,
sort of standard trick. It's a really nice trick. But if you've
okay.
got a constant that you want to swap for a boundary condition, you just take
Mm-hmm.
that constant and make it the time derivative of something, of a
Sure.
coordinate or a configuration variable that plays no other role, and then your standard Euler-Lagrange equations tell you this is a constant. So you can sort of
Good.
play that trick quite nicely.
Right, right. And you have wisely chosen not to put in an essential singularity here. That's nice.
Yeah, I mean, you can do that.
But
It's just you end up with a constant in there. Yeah.
Yeah, I'm still struggling to see how the action happened to be minus h. Is that a
Yeah,
oh,
so
okay. Yeah.
I mean, you can come at this in a couple of ways. The first is you can work out what the action has to be in order to reproduce the Euler-Lagrange equations on the invariance of the transformation. And
Uh-huh.
if you work through that, and that takes a little bit of work, it tells you what the action has to be.
Hmm.
But that's, that takes a little bit of doing.
Uh-huh.
The second way you can do this, which is possibly easier, but we don't have it written out neatly here, is if you work from the Hamiltonian side, you can work out what the dynamical similarity has to be there,
Okay.
and then see you do your Legendre transformation back again and work out what the action is.
Well, I have this hack right now, which is to look at the second Friedman equation and
Yeah.
then stare at 6.9 and do an integration and say, oh,
Yeah.
there's stuff that looks kind of similar. But
Yeah. I think you might be missing a minus sign, but yeah. Otherwise, yeah.
yeah, there's definitely
But
something
yeah.
missing. But
But
okay.
anyway, yeah. Sure.
That's the spirit of it.
Sure.
Okay, well, I can kind of believe it now. But I think that it is important, the second procedure that you mentioned, because there's some principle behind using the
Yes.
dynamical similarity to identify the invariance. And yeah, okay, so okay, let's maybe run through that in our heads real quick. So we write everything out in the Hamiltonian form,
Yeah.
then we figure out what the dynamical similarity does. We identify it's not going to be a Hamiltonian vector field. It's going to be a certain kind of vector field, which acts on everything. Because I mean, this will rescale the symplectic form. It's not going to be Hamiltonian from that
Mhm.
perspective. But okay, we identify that thing, and then we identify invariance under its action.
Yes.
Right now, where am I? At what point have I gotten to being able to identify A, like the action A?
Right. So this comes from how you transform from the symplectic structure to the contact form.
Good. Okay. Yes, because that is
Um,
the excess,
yeah.
as we showed.
Yeah.
Yeah.
So if you've got a symplectic structure on an even dimensional manifold, you want to reduce this manifold by 1 degree of freedom. You want to remove
Good.
one variable from this. You've got a vector field which acts on your phase space and joins up orbits under this transformation. And so you do the most obvious thing you can do. You just do a interior product of this vector field with a symplectic structure,
Okay.
and that will give you a contact form.
Nice. So what you're saying is I will. So this is the scratch pad for
Sure,
half-baked
yeah, no problem.
equations. So I have myself an x sub ds, and what it does is the following. Well, okay, it acts on stuff to rescale them, right? So it acts
Yeah,
on, well, stuff, which is, yeah, like, okay, you could have q dot q, whatever. And
yeah,
the action is like a scaling, which means that I have, again, some kind of 1 plus delta lambda with the hash in front of this, because I don't know what it is beforehand, of q, something else for delta q. So roughly there's going to be some action like this. Is that
yeah.
right? Q of dot q
I
and so
mean,
on.
yeah, sure. I mean, if we're going to jump to
And
the Hamiltonian side, maybe we should be talking about P's and Q's, but in any
oh
case,
sure,
it's
yeah. Let's not keep, yeah. Well, why are we doing this? Okay, so there's a p, there's a q, and now one would say, aha, there's a symplectic form, and here's a vector field. So shouldn't it be that this hash is related to that one? Hash 1 is related to hash 2 by some simple minus relation? And the answer is no, because there's yet another hash that appears when we actually apply this thing to the symplectic form, right? So this is not 0.
yeah,
It is in fact proportional to omega. It's basically
yeah,
lambda raised to yet another power of
yeah.
omega. right? So that's
Yeah.
kind of what dictates what these numbers are going to be, based on what this is going to be. Well, okay,
Well,
this is
there's
again, so it's
yeah.
again infinitesimal, so there's going to be like 1 plus something.
No, it's not
No?
infinitesimal, right?
Oh,
If it were
right. Okay.
infinitesimal, you'd want this to be 0 in the case of a standard canonical transformation.
Yeah. Okay.
Yeah.
Okay. Good.
So it
So
acts
that
like this on the symplectic structure, and it should also act on the Hamiltonian itself
in a similar fashion, yeah.
in a similar
So it
fashion to a
it
different
doesn't
number. Yeah.
kill that either. So there's like going to be H, and then that goes to lambda now to just a 1 star. H. Cool.
Yep.
Okay. Great. So
And
what we
so
have.
since this is a vector field, you can have, you want to normalize it because you don't want to sort of have multiple lengths along the same vector field giving rise to different structures. So normally the way I would normalize this, normal normalization, is to set your lambda double star equal to 1.
Great. So we set that equal to 1, and that's the scaling of everything else.
Yep.
Okay, great. Then, having done this, we look
Yep.
at, and that gives us eta.
Almost.
Okay.
So this will give you a contact form. But if you want a contact form written in terms of purely the invariance of this transformation, you have to divide by something that has transformation scaling of 1. So in other words, because so you want to take this divided by something I call rho normally because it's where rho is anything that transforms with factor 1 under a Lie derivative along x dx.
Right. Yeah. So it just goes to rho.
Rho, yeah.
That's what you mean by 1. Okay, good. Great.
And
So
you'd have to
that's
do a lot of sort of checking yourself, and this takes a while, but it doesn't matter what you choose as rho here. It'll give you a different form, a different functional form, but the dynamics are invariant.
very cool. So what I would have to do is identify the action of the dynamical similarity on the various phase space variables and Hamiltonian and so on, and then form the resulting Hamiltonian, well, the resulting vector field, contract with symplectic form, and then normalize it essentially. That would give me eta, and then I would identify. Okay, so then let's get to the action, right? So this is the contact form, right?
Yep.
Is this the contact form, or is it just the piece in it that's beyond the symplectic form?
No, this is the entire contact form.
Great.
So this is the
Okay.
nice thing.
Great. So then you're saying that in coordinates, this is plus omega prime, whatever, something like this. There might be some reshuffling of variables involved, so I call it omega prime.
Yeah.
Okay, I see. So eta minus omega has some. This gives you some sense for what the action should be.
Yeah.
Very nice. Okay, and so you can do all that and discover the following.
Yes.
You're saying in the homogeneous cosmology case, if I put all of this effort, you discover that you have H here. Very cool. Okay, so let's go through what you have here. Extremize the Hubble parameter at time t, subject to the acceleration equation, and given an initial value h and t. This should yeah. So that's just like kind of the trick of starting from here.
Yes.
And yeah. Okay, great.
But physically, it's interesting to note, right? Because this is something to do with minimizing extrinsic curvature subject to a constraint.
Yes.
Which might be a hint at how you do this in general relativity or more complex areas than just sort of the simple examples of cosmology.
That's actually very fascinating because now you're saying that actually, yeah, this is kind of an extremal surface condition of codimension one though.
Yeah.
Um, okay, okay, that's what I'm thinking about. Right. And of course, in general relativity, there's always going to be, the bulk of the actual equations of motion that come from knowing how the extrinsic curvature evolves
Yeah.
from one Cauchy slice to another. That's the messiest one. Because of course the adapted metric just changes by the extrinsic curvature, well, some linear combination of it and its trace. But then that thing changes by everything, the intrinsic curvature, some all kinds of wacky things. And
Yeah, I will
what
say
would
you
you okay,
don't
so
go into this looking for short calculations, I'm afraid. It's
yeah, but so what would the steps be just in sort of principle? So I have this thing, right? So I have yeah, k dot equals all the stuff that it equals.
yeah.
And then
And then it looks like the action is telling you to extremize k, right?
mm,
Integrated perhaps over a surface,
okay.
subject to maybe the Ricciardi equation or something like this, right?
Mm,
Again, this is speculation at this point because I've just seen this in cosmology and not in GR. Field theory is, as you know quite well, quite difficult.
right.
And so
Yeah,
applying
but
this to GR
yeah.
in general would be interesting. But yeah,
It would be fun. I mean, especially if we just go like, there's like some limit, or just set the intrinsic curvature to 0, right? You just like pick flat slices. I don't know if it's possible to
yeah,
do the extremization then, but you have that dot kij minus dot k gij, something
yeah.
like this equals k, k, um,
So you need metrics and that.
yeah. Um, okay, so you have some kind of simple, you have something like this, and then you would kind of do the various things. Well, this is completely scalar. It can't be this. There's something else going on here.
We're missing
So
it. Yeah,
this is like maybe the trace of that equation.
yeah, something like
Um,
this. Yeah,
yeah. So okay, I mean, there's an expansion of this involving all kinds of nasty shit, but
yeah,
maybe there's a way to proceed from there. Okay,
yeah.
we'll come back to that one day.
Sure.
It's not this day.
It's on the to-do list. Yeah.
Okay, cool. And there's also an equation for z, the
Mm-hmm.
thing that is close to being the scale factor. Cool. Okay. So okay, this is an interesting point because yeah, so you have the thing that is like the shape, and you have the thing that is like the scale
Yeah,
factor being the thing that is like the scale, and you say that you see, okay, you want to introduce the scale factor, you have to do it in the following way, but this isn't strictly necessary for the evolution of the system. So yeah, it can be completely integrated without ever referring to the scale factor. And that is sort of at the heart of your observations about the shape degrees of freedom as opposed to the scale degrees of freedom,
yeah.
right? So could you walk us through that in some more generality? So you're saying, okay, so we had this procedure here, right?
Yes.
Started, we found the contact form,
Yeah,
part of it was the action, part of it was omega. So
yeah.
now, yeah, well, what do I do? Like, how do I come
So
to
now
this
you're going to want to
conclusion?
contact Hamiltonian as well.
Okay.
And your contact Hamiltonian turns out to be just your regular Hamiltonian um, divided by, again, it's going to be rho to whatever power you've used. I think it's lambda star here, right? To make it
So it's rho to the power lambda star, or you mean the star
rho to
in
the
the
power
lambda?
of rho to the power of lambda star,
Nice. Okay. Well,
because
there's a
then you
lot of
find
stars.
that, yeah,
Okay. Okay.
um, because then you find that the Lie derivative of this along the dynamical similarity vector field is 0. Right? You can just check that.
Ah. Okay. Well, that.
So this
Okay.
is
That.
made up of invariants.
Oh. So this. Right, because of my, yeah,
Yeah.
okay.
So now
Because of
both
this and
your
this.
so both your contact Hamiltonian and your contact form are now made up of invariants of the dynamical similarity vector field.
Okay.
And so this now is a system that can give you equations of motion purely on these invariants.
Mm.
So if I want to know the equation of motion for example, the Hubble parameter lower down, I never need to make reference to rho, because rho or anything that scales with
Oh, I see. Okay.
x ds doesn't turn up anymore.
Oh, I see. So that's a key point, that this is where the scale factor went
Yeah,
in this example,
yeah,
right?
exactly. That's where your
Okay.
scale factor goes.
Oh, very cool. I see. As some kind of, yeah, because we were using A cleverly here to dictate the scaling of other things because it had the
Yeah,
linear scaling. But this is just one of these things is a choice, and presumably it's this one,
yeah,
right? And it's
yeah,
kind of
yeah.
inessential as to what exactly it is. And that goes back to what you were saying, that it doesn't really matter so much what rho is, provided you can find this property to hold, and then okay.
Yeah.
Okay,
And
cool, cool,
so
cool.
yeah, and so you can find the equations of motion from this Hamiltonian and contact form for everything that is invariant under these transformations. So we've taken a, let's say, 4 or 6-dimensional phase space, we've identified this vector field along it, and we've modded out by those transformations onto the invariants under that lead dragging along this. And then we have a system that then operates on this lower dimensional space.
Right. So you started with something that's even dimensional.
Yeah.
There's the scaling transformation and its
Yeah.
canonical conjugate. Get rid of the stuff that is its canonical conjugate, and then you're left with this contact stuff, and then you have, okay, great. This is
Yeah.
sort of a very clear picture.
But I should
Nice.
point out this is really different, right, from how you normally apply a symmetry transformation. Normally, if you were doing this, you'd get rid of not just the vector field, but you'd also get rid of its conjugate.
Correct. Yes.
So if you're doing translations, for example, you don't just get rid of overall position, but you get rid of overall velocity.
Yes. I mean, it's basically that you have moment maps in, like, you have the conjugacy between, like, you have some symmetry transformation, then you have a moment map, and then you're just looking at like the surfaces where like some moment map surfaces, for lack of a better word.
Sure.
So you're kind of effectively getting rid of that too. But here, that's not what you're doing, because indeed, this is not exactly a symmetry. It's not exactly what's going on.
Yeah.
And here you comment on other choices you could have possibly made.
Yeah.
Well, you could have changed the time parameterization, then that's the same as playing with what the lapse ends
Yeah.
up being, as it should, right?
Yeah.
That's what
Makes
the
no
lapse is
difference to the
for.
equations of motion. You just end up with a more funky looking system.
Very cool. So now we could maybe either proceed to the Kepler problem, or we could sort of jump into another place where something like this helps. It's your choice.
Well, given that you've made the second one vague and enticing,
Okay, let's maybe go there. Okay,
okay.
so I guess the basic point to make is that there's a way in which path integrals can turn into actual integrals. Like this is a jump, right? So we've really departed from the kinds of things we were talking about before. But basically, there are these systems where we can actually do the path integral, which almost always we avoid. Right? I mean, it's just you do integration by parts instead of doing an integration. That's what perturbation theory is. Or you find some other scheme to approximate it, or it's just a kind of inspiration, and you never actually do anything having to do with path integrals in the first place, right? So there's a slew of options as to what you can actually do with this formal expression. However, in certain scenarios, it's possible to turn the path integral into an integral, either a finite dimensional integral or into a matrix integral. And these are called sort of localization phenomena by and large. The engine powering them, right, the trick that lets you do it actually has to do with being able to rescale either the action or a term in the action, right?
Okay.
So this is kind of maybe ringing a bell.
Yeah.
So let's just take a look at a simple example, and then we'll go to a sort of another simple yet maybe a little bit more fun example. So here we're not talking about path integrals at all, right? So this is from certain notes I found, which are actually really good. So it's about like supersymmetry in Morse theory, how, or in other words, why supersymmetry is Morse theory. But we'll go into basically the aspects of localization. So let me go. Yeah, great. Let's jump right here. Great. Okay, so what we're going to do is a mixed regular and Grassmann integral. I don't know what h is, which is what makes this regular integral hard. I know that it is Grassmannian in the, well, it's Gaussian in the Grassmannian variables, which is what makes it easy, right? Okay, so then you see that actually, okay, so there's a symmetry relating the bosonic and the Grassmannian variables, which is the sort of poorest man's supersymmetry. And it really is not an exaggeration to say that this is exactly the format in which supersymmetries writ large appear. You know, like when they help you in exactly this way. You can show that this particular format, so square of h prime minus h double prime, all multiplying psi bar, is invariant under the supersymmetry identified here. But here we go. We do a rescaling of h, right? This is almost like dynamical similarity, except only if you looked at the second term, right? So it's an overall rescaling only of the second term. The first term scales sort of like the square, right? But what you have is that dz d lambda as in any observable is invariant under the scaling. And to see why, notice that you take the derivative with respect to lambda, you bring down the following object. This object is actually the supersymmetry transformation of something else. So the reason why, so the reason why you can do it here is because the term that's getting scaled is actually q of something else. Right?
Yeah.
The reason why it helps for it to be q of something is that you can pull the q essentially all the way left, meaning you can write it as q. So here is basically the point to say that it's q of something else, but then you can actually pull this q to the left of e power minus s. The reason you can do that is q squares to 0. If this was a regular symmetry transformation, it doesn't help very much because you can't do that, right? Like you have like symmetry transformation composed with another symmetry transformation is yet another symmetry transformation. There's just an algebra. Q is cool because it squares to 0. QS is 0 and it squares to 0. So what happens is that there's this exactness, right? So basically dz d lambda is 0 because of all these fun facts having to do with this being a fermionic symmetry.
Yep.
That means z evaluated at 1 and z evaluated at infinity are equally good.
Yes, right? Sure.
Nice thing about evaluating z at infinity is that you basically have the dominance of this term, which then gives you, well, okay, so you basically have a Gaussian integral with this being the linear contribution. Sure, and this kind of dies away, and all you're left with is going to be the following. You're going to have a Gaussian integral where all the lambda dependencies essentially cancel, and you're going to have h double prime divided by h, sum over all the critical points. This is the index of h as a map.
Okay.
So z is just a sum over 1 or 0, right? So it's just a sum of 1s and 0s of h.
Yeah.
This is all just addressing, right? So that's the sense in which supersymmetry. Okay, so you say like, oh, how? Okay, here's a fun fact. This is the pure potential contribution of a quantum mechanical system. So that happens in the next whatever. There's blah, 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 blah. Nice cohomology, this and that. But okay, here's the quantum mechanical model, right, with time derivatives, and the same thing that we had before, right? It's just a potential term.
Yeah.
But
Yeah.
note, okay, so there's this funny thing called the Witten index, which in supersymmetric theories is what the path integral with periodic boundary condition computes, as opposed to the partition function. That's just the terminology. It's cool that this index happens to be an index. That's why it's called an index. It's not very, it's not very illuminating. But the point here is that you see, you either look at this as the quenched limit, or you go and compute the fluctuation determinants, right? Like, if you actually looked at this action, you can, in principle, do the quantum mechanical equivalent. You go to Fourier space, try to compute what it's going to be, right? And what you'll find is that you get a ratio of determinants, but then that ratio of determinants again boils down to this.
Okay.
And this is basically like how those radiative corrections of all those fluctuations canceled amongst each other, because it was all addressing of the index to begin with. You see, like it's kind of like what you would otherwise call the radiative protection of degrees of freedom under supersymmetry. Is like why people say, oh yeah, I know, supersymmetric objects, they're cool.
Yeah.
It has to do with the fact that it's always computing something like this. And here there's actually a much cooler example having to do with something called the Poincare, what's his name theorem. We'll get to.
It's a very technical name, that
Vas. So there's Marcos Mourinho, who's been featured before on this podcast, as in not him himself, but his lecture notes. And these lecture notes are sort of about the most powerful application of these methods, where you're converting calculation of some field theory, like supersymmetric field theory, turning that through localization into a matrix integral. So that's kind of like, one of the most powerful examples of it. But there's like the simple example he shows here in 34. The reason I bring this one up is that it's a case where the actual okay, I'm searching for it in a silly way, but bear with me. Oh, sorry. Maybe I back a bit. Page number 34. Let's get it. Yeah, there you go. Great. So the reason I bring it up is I think it's a case where you actually have the action as a whole transform. But okay, so the general prescription is like, this is why I said before we started recording that this phenomenon relies on something like dynamical similarity, but only for a part of the action.
Yeah.
Not the action as a whole. So what part that is actually a part that sits under a delta, which is like the Q, some Grassmann odd symmetry generator. It doesn't matter that it's a supersymmetry. It could be BRST, right? But ultimately you have a Grassmann odd symmetry generator, which squares not necessarily to zero. It could necessarily be that it's like a symmetry, a Grassmann even symmetry. But when you take the following, right? When you take e power minus s minus t times delta v, where v is some Grassmann odd operator, take the delta to make it even because the action is even. Then what happens is you take d over dt, you pull down delta v. But because it's delta v, you do that. Yeah, and you see, exactly. Great. And so that's the key behind this trick. And always you're just pushing this thing to infinity. Now the reason, like what this is you're just saying h bar controls the strength of quantum effects, for lack of a better word. Now our friend Julian would say there is no such thing as h bar doing anything. You have h bar measured in units of the action, or action measured in units of h bar. So there's some dimensionless combination of coupling constant say to h bar. That's the dimensionless thing that actually controls the strength of various interactions or quantum effects, for lack of a better word, right? And in the limit where h bar, as in this rescaled version of h bar, goes to zero, you're pushing the dynamics towards a classical solution, right? And that's exactly what the ability to put an overall rescaling in front of the action lets you do. You can just tune that up to infinity, right? And then you're forcing the path integral down to its quantum, down to its classical limit, plus maybe fluctuations.
Limit, right? Yeah.
With fluctuations. So you can have one loop, right? So there's a normalization you haven't fixed, and that's given by the one loop partition function.
Okay.
But now we'll see something super fun, right? I think that this is an example where the whole action ends up being rescaled or not. We'll find out. Okay, so here, it's just as a nice math result that I never appreciated. I used to see this result. I never understood where it came from. I would just believe people. Here's a way to actually understand it. So it's a quantum mechanical system. It's sitting on a curved manifold. So it's an extension of a geodesic action by some Grassmannian degrees of freedom. Format is always X changes to Grassmannian, Grassmannian changes to nothing, Grassmannian bar changes to Lagrange multiplier changes by nothing.
Yep.
So that's like, this is like a format for so many different systems. Like it almost always appears. Great. Now, the action is delta of something.
Okay. Yep. Yeah.
Great. So that something is Grassmannian bar B plus some vector field V plus Christoffel symbols with all the indices contracted by the only things the indices can contract with. So that's it's suggestive. It's basically like some dressing of a geodesic action by some extra Grassmannian variables.
Yep. Yeah.
Okay. Right. And so you basically find that you can eliminate B in favor of V minus this mess of Christoffel symbols. And what you just get is the following action. And okay, so you basically can then introduce the inverse field bind, and you get something that you would normally call you would just normally call this a geodesic action with some extension involving tangent space information that is captured by the Grassmannian coordinates, right? So if I eliminate all the auxiliary stuff and the Grassmann bars, what you're left with, okay, and then you introduce a Vielbein, what you're left with is something that looks like, regular geodesic action plus tangent space information, right? So you have the information about geodesic deviation, and you have some more sort of like local information. And so psi you should think of as a placeholder for a dx, right? So there's like this relation between Grassmannian things and differential forms, like it's kind of obvious. Yeah, of course, there's always going to be, right? And so the information about like tangent spaces is always captured by stuff that's proportional to psi. So side of the first power, side of the second power, right? Like side of the first power would only know about like this, the covariant differential of V. However, side of the second power would know about deviations, right? Like geodesic deviations. Because it's dx. So that's all this is, right? It's just like you just took you just supersymmetrized the geodesic action by introducing some tangent space information. That's essentially all it is. There is a nice paper by Witten that relates Dirac cohomology and supersymmetric quantum mechanics, which makes sense of that statement. I mean, everybody is like, oh, what are the two things that always seem to square to zero? Well, wedge products between the same kind of thing and Grassmann numbers. Oh, what if they're the same? That's really the extent of the. I mean, I'm trying making it sound trivial. It's not trivial. It's actually a very deep insight, and it was one of the things quoted in his Fields medal thing. When I think it was Atiyah that mentioned one of these things as being the reason he won this Fields medal. Okay, now you see. Play the same game with localization after having eliminated half a dozen things, but note that all of this came from delta something to begin with, right? So here it's just that eliminating stuff makes it easier to identify a simpler piece that you can do the integral over. And, okay, so there what happens. You take t to 0, t to infinity. When t goes to 0, right, this delta v part involving this goes to 0, and all you're left with is this Riemannian, the curvature 2 form, quadratic size, and this integral over x. That gives you integral over x, or the volume form on space-time, times the Pfaffian of R, which is also called the Chern class. So it's R, which R, which R to even powers, right? So it starts with R, then goes to R, which R in 4 dimensions, and 6 dimensions goes to R, which R, which R. So that's awesome. It's the Pfaffian of R, right? Now, what is the thing that happens when we take t to infinity? Well, then we want to do the Gaussian integral, right? The Gaussian looking integral. So there you do an expansion in local coordinates, you do some rescalings, whatever. And what you discover is yet another index, right?
No,
so this is the so-called Poincare-Hopf theorem, that the equality between this and the Pfaffian of R. right? So this is the
Okay.
Euler
Yeah, yeah.
class is identified basically with well, okay, so H is like, this is the index of the vector field, right? So H is a matrix given by the derivative of V mu, the component
Hmm.
at some point, at point K. And then what you're computing is basically the determinant of this divided by the norm determinant of this, right? So it's like saying, were this like a scalar, like a map, then you would think of the index being related to the signs of the eigenvalues of the Hessian.
Yep.
But since
Yeah,
it's
yeah.
a vector field, it's enough to take one derivative, right? So that's how
Yeah,
you get
sure.
this. And so you get this crazy theorem, right? Which I would always see, like, Wikipedia has a less notation cumbersome representation of it. So let me just go to Wikipedia for
The
Poincare
eternal
Hopf
source, yeah.
theorem. Yeah, so basically, you see, you have a vector field,
Yeah, yeah.
and the sum over the indices of the vector field is given by the Euler characteristic.
Yep.
And
Yeah, yeah.
that, in some sense, is intuitive, right? But then the Euler
Yeah.
characteristic is this integral over the Chern class, right? Like this integral over all of these, like, Pfaffians of R, as they're, as we saw here. And
Yeah.
if you left me with textbooks and a million years, I don't think I'd be able to prove this. But with a little bit of trickery, especially involving the scaling argument involving, S,
Yeah.
that's very easy to prove. So
Yeah,
that's
no,
kind of,
that's a really neat little trick.
but this is also what I'm wondering when it comes to dynamical similarities in the path integral. They're either anomalous, right?
Hmm.
Or when they're instantiated, there are degrees of freedom that truly don't receive radiative corrections. And in the context of cosmology, this is particularly interesting because the whole question of whether the mini superspace approximation makes any sense rests on what the fluctuations do.
Yep.
And if you
Yeah,
could
yeah.
show, like, the only hope I see there, that this is just literally the only hope I see to give any concrete meaning to what people call mini superspace quantum cosmology, which is mostly done because you can, right? Like that's
I
usually the
mean,
argument, and fair enough. But if you wanted to know in a sort of principled manner why you can, like, how much of that survives once you introduce fluctuations, I think that the best hope is to have some argument for the protection of whatever you compute, whatever observable you compute under these corrections by the fluctuations. And I think that if you can sort of put in an argument like this, you see, because
yeah, it
here,
would be quite neat.
yeah.
I'm not, I mean, one of the issues is that I will add that to my ever-growing list. Um, I will say one of the things that I found of late is my to-do list has developed a horizon. If you go onto my to-do list below about entry 7, more stuff comes in above and things move up. So I'm afraid it
Well,
might
we can
get
put the
washed
call
away
out.
to infinity. But yeah,
Yeah, we could put the call out, if there's
yeah,
anybody
yeah.
out
No,
there
that would be
who's
interesting.
motivated.
But yeah, I mean, it would be, you're right, because the standing of mini superspace approximations is well, I mean, it's vital to most of the approaches to at least the Hamiltonian side of quantum cosmology.
True. Yeah.
The canonical quantum cosmology, the loops crowd, for example. You need this.
Yeah, well, the thing is that in that formalism, it's very hard to argue about how to get it out of the broader thing. I mean, it's subtle. Like, there are many papers written where people go back
Yeah.
and forth about that. In a more sort of like effective field theory point of view, you could say, it's not a ridiculous thing to do. I mean, we do it all the time. If you think about the quantum effective action, that thing is just, all it knows about are zero modes. If you pay
Yeah,
attention
yeah,
to, like, the one
yeah.
loop quantum effective action, it's a zero mode thing unless you start to introduce derivative corrections, right?
Mhm.
But like, you can compute the beta functions of QCD, right? The one loop beta functions of QCD, knowing only the zero mode structure of the theory.
Right.
That's
Yeah.
what you do, right?
Yeah, yeah.
And nobody really faults you for doing that. So it's not an altogether ridiculous thing to do. What needs to happen, though, is that there has to be some understanding of why the derivative corrections are suppressed, or to what extent they are, And that's where I think it would be very cool to have some argument like this if it works. You know, like I don't know if it
Yeah,
works.
yeah. I mean, yeah, I mean this is, I mean, this brushes over a gaping issue, right, in making the transformation from this as a classical symmetry to a quantum mechanical symmetry. Um, because if you take this very, very seriously, you have to be hellishly careful by what you mean by H bar.
Right, but also
Um,
you would have to know. I mean, essentially, it boils down to whether that symmetry is anomalous or not. When you take the action by that vector field and try to promote that to some kind of
yeah.
operator, presumably, also, I mean, my intuition just tells me that whatever your scaling weights are, D would commute with itself, right? It's like it's a scaling transformation.
Yeah, yeah, yeah.
Those are essentially abelian, but that doesn't have to be true in the quantum theory.
Mm-hmm.
And if there is an anomaly, that's one way to explain what happens, right? And that's actually fascinating because you can tie all of the interesting quantum effects to cohomological properties of the operator, of that dilatation
Mm-hmm.
operator. That's fun. And there is a paper by Matteo Lastaglio and Flavio Mercati from like 2014 or something, where they talk about quantization of some mechanical system where it has a classical scale symmetry that becomes anomalous
Mm-hmm.
at the quantum level. And they have a fun story about how you can now use this as a true Hamiltonian in your in your quantum theory or something. So that was kind of the push they were making. But I
Yeah.
think that should certainly be re-examined in light of the dynamical similarity story, because it does. I mean, as you're saying, you should be very careful about what H bar means. But essentially, if you just knew about quantum theories. I mean, the way I think that the right way to think about this is backwards. All you know is actually about the quantum theory. There are some observables that behave in a certain way. There's some states that kind of have a simple dynamics, and you call that classical,
Mm-hmm.
maybe. Okay,
Yeah.
fine. But really, the only thing distinguishing classical from quantum is, you know, what appears where, like what's appearing as like if you just took this form out of the path integral,
Mm-hmm.
you find in quantum mechanical systems that it always boils down to a certain kind of series. It's a series in H bar measured in the units of the coupling or vice versa. I mean, it's
Yep.
your choice if you want to call it a series in 1 over H bar or in coupling to positive power, right? So it's like
Yeah,
or
yeah.
coupling to some, yeah.
Yeah.
But there are instantonic corrections. So it's a series. It's not just a power series. There's also
Mm-hmm.
exponential minus something over the dimensionless H bar to some power, like those kinds of corrections. Quantum
Mm-hmm.
mechanics, it seems that that's all there are. And how close you are to being dominated only by that exponential factor tells you how classical you are, right? So that's those instantons are just backgrounds, classical backgrounds. And that gives you, like an invariant way of talking about what classical or quantum means, right? There's this trans series, and what are you accessing, right? Are you able to access the stuff deep into the power series, or are you just sticking close to the evaluation? Like, is the observable just sensitive to the evaluation on that saddle point, right? So
Yeah.
that I think is something to, yeah, bake into all this. It'd be very interesting to understand um, to what extent dynamical similarity is dictating such things. Because another thing that rhymes with mini superspace is general sort of moduli space analysis. Because what are moduli spaces? They're mini superspaces for instanton configurations.
Mm-hmm.
And at least in quantum mechanics, it's like kind of universal as to what their contributions are. You have like multi-instanton configurations, which necessarily give rise, like these quasi-zero modes, right? So the mini superspace degrees of freedom always give rise to certain logarithms in this trans series. In addition to these, in addition to the terms I mentioned, you have certain logarithms. And yeah, I mean, it's like, yeah, I'm just curious to understand what subclass of this format of trans series these dynamical similarity exhibiting systems fall into.
Well,
Is
I'd
that that would
suggest
be?
you've got yourself a research project there, Vasu.
Yeah, well,
Um,
I don't have a horizon because of the reason you do, but I have a horizon just because I'm kind of lazy. But yeah, no, absolutely. It'd be fun to like think about these things. And yeah, I mean, like whoever's out there listening to this, bot or not, I'm happy to collaborate.
Hey, if AI can solve, yeah, these
I mean, they have to
issues,
do
I'm
something
quite
on the
happy.
like on the off season. There's no elections, so what are they doing?
Yeah,
They need
exactly.
something to
Yeah.
do. So come solve these physics problems with us. Yeah, so I guess I'll also throw in the references, the other references you sent me about all this.
Sure.
And we have not really, we've kind of scratched the surface of this entire topic. We haven't
Yeah.
talked about some of the sort of highlights. One of them, at least from my perspective, is the result where you can show that there are cosmological settings where the invariance that we discussed can kind of just not care that there was a Big Bang, right? That's
Yep.
that's maybe
Sure.
one way to put it. They can kind of just there's not really sensitive to the fact that there's a singularity. It was in the rho, like the equivalent of rho, that there was the singularity of the Big Bang. That was is
You
that an
can
accurate?
you can sort of think about it that way. Yeah. I mean, what you do is you can construct within homogeneous cosmology, so anisotropic solutions, for example. I mean, you can do it in
Right.
the Friedmann solutions as well, but there are the BKL conjecture, for example, says that when you get close to a singularity, you're well approximated by these homogeneous Bianchi models. And so what Tim and Flavio and I did was found that if you work, I mean, we did this very sort of indirectly. We didn't realize the relation to dynamical similarity till after. But if you work with the set of invariants and you look at the evolution of the set of invariants in a specific topology, you have to be a bit careful about, you find that all the issues that arise at the Big Bang aren't there anymore.
Mm-hmm.
So as a sort of, if you think about your evolution as a Hamiltonian vector field on your contact space, this Hamiltonian vector field just continues quite nicely beyond that point.
I see.
And so you'd say that the classical solution here, modulo this dynamical similarity, hasn't got the same issues that the usual sort of Einstein-Hilbert system does.
Mm-hmm.
And so, yeah, what we showed, and I've done a few papers about this afterwards in various different systems, and my grad student and I are working on sort of the grand version of this. But essentially, what you find is that where there are these singularities, they're singularities due to scale, but the
Mm-hmm.
system knows nothing about scale.
Right.
And so, sort of, by throwing away that part and saying, look, the only reason you know about scale is because you put this in by hand in the first place, you can find that there's a really interesting dynamics there. In fact, it's the kind of stuff you'd be quite interested in, because you take your initial configuration space, let's say, and your
Mm-hmm.
configuration space is normally R to the n,
Okay.
and scale is normally something like R plus.
Yes.
You take R to the n mod R plus, and you're onto real projective space.
Yeah.
And then your real projective space, you can do a multiple cover of it by an SN. And then you find that the equators of your SNs are the infinities of your pre-projected space, so your R to the n.
Nice.
And so
Yeah. I mean,
you have this rich structure that still exists at infinity, and it's a regular point on this projective space. And so you can look at dynamics instead of doing dynamics on Rn. You look at dynamics on projective space, and then form the phase space over the projective space, and so forth. And that
it's
remains well
nice.
defined.
That's very interesting. I mean, I would recommend you liberate yourself from real projective geometry, which is hard, and go to complex projective geometry, which is the bread and butter of algebraic topology or algebraic geometry. And I feel like maybe that's another fun exercise.
Well,
Another
you can
reason
make
to do
life
that,
easy
though.
by just to say you make life easier by working on an SN, right? Because
Sure,
your N
that is
sphere is
true.
a
I mean,
is a
yeah,
multi-cover of a projective space, so you could just work there.
true, true. For most purposes, I guess that is adequate. But the reason I'm mentioning complexification is that there's a sense in which um, a lot of dynamics, like tunneling dynamics and so forth, can just be seen as classical dynamics on a complexified configuration space.
Yeah, yeah, yeah.
And so this is again tied to the story I was mentioning before with the resurgent trans series and whatever, is that the way to see all that from the path integral perspective is to complexify as much as you can. And it would be very interesting to see what one can do there. Yeah, so have you like so the kinds of systems that you're looking at, like what is the prototype potential, or like what are the kinds of potentials you're interested in? Are they mostly like homogeneous functions, rational functions?
So yeah, I mean, so my potential, sorry, my camera seems to have gone all blurry. I don't know if you can still see me.
Yeah, I can see you. Yeah,
Okay,
now you're back.
so okay, good. Um, so in homogeneous cosmologies, the system just looks like the dynamics of a particle subject to a potential, and the potential is exponential in the configuration space. It's a sum of some exponentials. This is what we call the shape potential. In fact,
So
it's
it's
entirely
exponential in the configurations. Okay, that's interesting.
yeah.
Go on.
In fact, it's entirely determined by the topology of your spatial slice. And so you can look at these sort of these Bianchi models, and you can sort of work through these, and it's a medium exercise, probably a week or so for a grad student to work out exactly what these things are.
Mm-hmm.
In the cases of scalar fields, which are, if you're a cosmologist, you love scalar fields because scalar fields are just easy. So long as your potentials fall off faster than some exponential. So in other words, unless your potential goes up like e to the phi, you can deal with these. These become negligible terms as you approach the singularity.
Interesting. I see. Yeah, well, the exponential just reminded me of Liouville theory and the Liouville mini superspace, which also, famously has these exponential potentials.
Yeah.
But I see. I guess you're mostly thinking from the perspective of cosmology, but I was more
Yep.
wondering because when you have things like sine Gordon, double well, or whatever, there's a wealth of calculations people have done using what's called exact WKB, where
Mm-hmm.
there's a sort of very complete characterization of the quantum dynamics of these systems, right? So
Yeah.
it's some of these are cases where it's not that easy to actually solve the Schrodinger equation, but
Mm-hmm.
you can still develop this kind of trans series understanding. You have an understanding of what all the various multi-instanton sectors are, and yeah, I mean, like whatever I was mentioning is kind of very apparent there. And naively, out of what I would have tried if my intention was to get a better understanding of the interplay between dynamical similarity and say quantum effects, is sort of like bake into one of these potentials some kind of dynamical similarity, like see what the minimum modification that I need to do is, and then see what the effect is on the resulting wave functions, which are all kind of pretty well characterized and pretty well known. But similarly with the
Yeah.
Liouville mini superspace, which has an exponential potential, there is an understanding of what the wave function is. I don't know if anybody subjected it to the exact WKB, nor if it's really needed, because exponential potentials don't tend to do. There doesn't tend to be all that much tunneling happening.
Yeah. Well, I mean, again, there's some groundwork to be done before you can even get to that level, right? Because again, the quantum mechanics of an odd dimensional phase space is not easy.
Right. Well, yeah.
We you're
Yeah.
not just taking your Poisson bracket and promoting it to a commutator because something doesn't have a canonical conjugate. So
Right, right.
life does become more complicated than you might initially think.
Yeah, I
Um,
was more thinking you just irreverently stick everything into a path integral. That's
yeah, but again, because you don't have Liouville's theorem anymore, your integral kernel is no longer sort of neat as well.
true.
So you've got to
True.
be
I mean, that
careful
is
about
annoying.
that.
Yeah.
And you have to be very careful you haven't introduced some artifact in your parameterization or something if you do this. So it's not, you can't just sort of blindly dive into it like that, because I think, well, I mean, maybe you can, maybe it'll work, but
It isn't what you would do, is what you're saying.
yeah,
Okay. That's fair. That's fair. Well, this was fun, Dave. You've been very
cool.
generous with your time.
Not at all. It's
And
always fun to talk. Yeah,
yeah, well, there's a lot left for us to discuss, very honestly. And
sure.
I'd even be open to an ensemble cast at some point with some of your fellow shaper colleagues, and
Yeah, sure. That'd be
it'll be
fun.
fun to yeah, fun to get a discussion going. But anyway, if you enjoyed this and got this far, please subscribe, like, leave a comment, and share. This is Theoretically Podcasting, and I will catch you next week.